As I said, some of you probably figured out that when we linearize equations, typically we go on to look for waveform solutions. So we ended up with these equations in terms of perturbation velocities and perturbation sea surface height with its gradient, zonal, meridional, and the vertical equations. And something to note here, I realized that I had not set the sound to this headset in the previous two podcasts, so it sounds a little different because it's taking the sound from the computer microphone. So it sounds a little different. I hope it's still very audible. I checked, it seems okay. But if you're unhappy with it, send me a message. I'm not going to re-record it right now. Okay. So in this equation, if h bar, the mean depth, becomes very large, then it can become the dominant term, which means this balance can happen with just these, which means du prime dx plus dv prime dy has to go to 0, become very small, right? So that's something which means what? The flow is non-divergent and barotropic. So we have seen that the tropical systems can be barotropic, and Charney had trouble explaining the dynamics by making the wrong assumption of the scale. Nonetheless, we saw how baroclinic processes are generated by heating and the coupling to the vorticity equation and so on. Because coefficients of 5.8 are independent of x and t, we can then write these solutions as sinusoidal forms in longitude and time. So v prime, u prime, v prime, h prime as functions of x, y, t can be written as u, v, h, y times exponential kx minus omega t, where we have the waveform, and r here is that it is the real part of the solution that is of interest for us. This is the normal mode equation of the system we have here. Just to repeat the definition of normal modes from the book and not elsewhere. Normal modes describe the oscillations of a system and represent an oscillatory pattern of motion where all parts of the system move sinusoidally relative to a fixed phase relationship. Okay, so there is no relative motion of the different components of the system. And each normal mode is independent and orthogonal, and one normal mode does not introduce another one. It does not produce another one. So they are independent and orthogonal in that sense. Okay? We will see what that means when we come to the physics of it. So you can now use this transformation. I think now you need your knowledge of linear algebra and eigenfunctions, eigenvalues, and eigenvectors, and so on when we do these sorts of transformations. So now we have the Doppler shifted frequency here, which is written as omega minus k u bar, our background geostrophic flow. This is essentially a vorticity term again. So this du bar dy is the relative vorticity, and this is the planetary vorticity advection by the meridional perturbation current, and this is the mass term or the potential energy term. Then you have the Coriolis wave term and the height change in the y direction, which is going to perturb u prime, obviously. This is the gravity wave speed squared, so square root g h bar squared. Again, this is the mean flow Coriolis being affected by the meridional perturbation and so on. Okay, so just get comfortable with these terms. So we can form now a single equation here in Vy, the meridional direction, by eliminating the zonal wind component u and the height h. That's the goal. The algebra is rather tedious, as the book says, and is summarized in Appendix D. It's moved out. First of all, we are running through the equations so that when we come to the physics, we don't have to worry about the derivations of the equations. We get that out of the way. and then the derivations themselves are so complicated and tedious that it is moved to Appendix D, but you may not open the appendix at all, so I'm going to run through the appendix here. And the final general form of the equation in Vy for arbitrary u bar equals u bar y, so meridionally varying zonal geostrophic current related to the meridional slope of the free surface is going to be the goal here. So we are basically trying to derive the wave equation 511, which we will come to. So you are going to do some simple manipulations. U is eliminated from equation 510, the zonal momentum equation, by multiplying 510a by beta y, the Coriolis term, and the Coriolis effect, Coriolis factor, whatever, f, 510b by I omega d, the Doppler shifted frequency, and produce the first of the two equations which are in V and H. Again, vorticity, wave number, Doppler frequency term, and so on. The second equation in V and H is going to be obtained by multiplying the zonal momentum equation by kc squared and the vertical equation by omega d, and we get the second of the V and H equation. So we will solve for GH. To find that, IGH is this complicated expression which turns out to be the phase speeds, dispersion relations, and so on. We'll start relating to the waves later on, and these momentum and vorticity terms. You can now see the interactions between the waves, mean flow, and this is the kinematics we were trying to get ready for, and these equations are really quite complicated, but they will give beautiful wave solutions when we look for them after we derive equation D11. Okay. To obtain expression dgh dy, we differentiate d2 with respect to y to give, after some manipulation, this very long equation. Now you know why this was moved to the appendix. I don't even want to say much, but just stare at it and make sure you at least recognize all the terms, the background flow, the gravity wave speeds, Doppler shifts, meridional and zonal perturbations, Coriolis terms, vorticity terms, etc. So we then substitute D3 into D4, and again after much manipulation obtain this. So equations move to the appendix, but even appendix is not going to go through all the steps, but just jump to this equation, which is now in V. Right, so you have u bar, no h here, just v is the main term, and that's what will give us the general form of the wave equation 511. So there is the function of y in terms of vorticity and momentum. So qy is this term, and that allows us to write this, which I will come back to in the next podcast. So I just wanted to run through the appendix just to show you how complicated the equations are. And even if you're doing applications of tropical atmosphere and ocean dynamics for your hydrology research or your ecology research or whatever, you can just be comfortable in knowing the equations, so that when you come to the physics later on, these equations make more sense. Physics is always beautiful. Math can be tedious and complicated, but we have to deal with it just to enjoy the beauty of the physics, right?